Good day. Today we're going to discuss the joint distribution in the probability theory. So we are going to describe the joint distribution of random variables, example of which is the distribution of random vectors. So let's have the first slide. The joint distribution of two random variables. By definition, the joint distribution of two random variables x and y, or also called as the bivariate distribution, is a set of probabilities in which the probability of x is greater than or equal to the set x, and the probability of y is greater than or equal to set y for all x elements of the real number and for all also y element of the real number. Okay, so when we say joint distribution of two random variables, uh, given two random variables that are defined on the same probability space, the joint probability distribution is the corresponding probability distribution on all possible pairs of outputs. The joint distribution can just as well be the considered for any given number of random variables. So, in other words, uh, the joint distribution is defined by the cumulative distribution function. So let's try to write. So the cumulative distribution function would be you have you will have uh, the function of x and y would be equal to the probability of uh, x greater than or equal to the set x, and the point y is greater than or equal to the set y. Or this is also known as the bivariate cumulative distribution function. So a pair of random variables xy, the xy must be capital letter, in is said to be a random vector. The corresponding joint distribution can also be called the distribution of vector. Okay, so there is similar definition for n greater than or equal to two random variables. Okay, now when we are talking about joint distribution of n random variables, okay, or also known as the multivariate distribution, you have here the set of all x, okay, sub I from 1 to n is the set of probabilities in which you have here the probability of x sub 1, the point x sub 1 is greater than equal to set x sub 1, and then the probability of point y sub 2 is greater than equal to set x sub 2, and so on up to x sub n greater than equal to the set x sub n for all x sub I elements of the elements of the real number. So, in other words, the joint distribution is uniquely defined by a multivariate um, cumulative distribution function. So, in this case, our multivariate cumulative distribution function would be this one, uh, x sub 1, and you have x sub 2 up to okay, x sub n, which is equal to the probability of okay, x sub 1 greater than equal to x sub 1, okay, up to okay, x sub n greater than equal to x sub n. Okay, so this is the multivariate cumulative distribution function. in ordered set of n random variables uh, from x sub 1 up to x sub n can be considered as an n-dimensional random vector x with the components x sub 1 up to x sub n. Okay, so to make it more convenient for the method of linear algebra, it is usually assumed that the random vector is a vector column. So example of it is a mapping of, okay, example of it would be a mapping of the set X, okay, of the sample space maps onto the real number in n dimension. Okay, rather than a mapping, okay, of uh, the set X, okay, which has a mapping of sample space onto uh, real numbers with the dimension of n by 1. Okay, so similarly, the random matrices can be defined as the it can be defined as the x, okay, the sample space, okay, onto the real number with n by m dimension, or the matrices with the random components. Okay, so let's talk about discrete random vectors. So suppose that x and y are discrete random variables defined on the same sample space, and that they make on values x sub 1 up to x sub n and so on, and y sub 1, y sub 2 up to y sub n and so on respectively, uh, from some finite and countable sets. Their joint frequency function or joint probability mass function would be the probability of xy, okay, is the probability of xy is equal to the probability of the x is equal to set x, and then y is equal to set y. Okay, which is in uh, it can also be considered as uh, the distribution of random vector xy. Okay, so uh, a discrete random vector is a random vector that can take either a finite or an infinite but countable number of values. Okay, so a k by 1 random vector x is said to be discrete if and only if the set values it can take the set of values it can take has either a finite or infinite but countable number of elements, and there exists a function uh, p of x, okay, or probability of x, which the uh, the r in k dimension, okay, relates to the set 0 1, which is called the probability mass function, such that where the probability of the point x is equal to the set x is the probability that takes the value. Okay, so that's it. Now, suppose that we wish to find a frequency function of y from the point frequency function. So we have, so here we have the probability of y sub j is equal to probability of y sub j is equal to is equal to y, and then the probability of the y sub j is equal to y, and x sub 1 is equal to x, plus so on, okay, up to uh, the probability or the p of x sub n y sub j. In other words, to make a frequency function of y, we simply sum down the approximate column of the table. For this reason, The P of y is called the marginal frequency of y. Similarly, summing across the rows would give us something like this. Uh, you have the P of x sub I is equal to the probability of the set x, which is equal to point x, okay, which is equal to the probability of x, which is equal to x sub I, okay, and then y is equal to y sub 1 plus the probability of x is equal to x sub I, y is equal to 1 half, so on, which is equal to the p of x, which is equal to x sub 1, uh, y is equal to y sub m, which is equal to this manner, which is generally equal to p of uh, x sub I, y sub I, y sub 1 rather, plus the probability of x sub 1, y sub 2, plus so on, plus the probability of x sub I, y sub m, which is the marginal frequency function of the x. Okay, let's have an example. Okay, a fair coin is tossed three times. Let x denote the number of heads on the first toss, and y denotes the total number of heads. Okay, so the samples in this case, we can construct a sample space. Our sample space would be uh, all heads. Then you have two heads, and you have uh, one head, uh, one tail rather. You have two, uh, one tail, then two tail, TTH, and all tail. Okay, so we see that the joint frequency of XY is something like this. So if we are going to construct, okay, 0, 1, 2, 3, then this is 0, this is 1. Okay, so out from the okay, out from the total sample, what would be the probability that you get one you get no head and no total number of head. So in this case, all tails. So that is 1/8. Okay. And then you could have one you could have one tail, one head, but no head and first row. So that would be okay, 1/4, and then this is 1/8, and this is 0. Okay. Now this would be 0, this would be 1/8, and this would be 1/4, and this would be 1/8. So if that would be the case, then the probability of y, okay, of 0, okay, is equal to 1/8 plus 0 which is equal to 1/8. So now, if we are going to get the probability, okay, of, okay, x, which is equal to 0, then you could have, uh, you could have, no, 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 no. Let's have, if that would be 1, okay. If this would be 1, then you have, uh, 1, okay, 1/4, 1/8 rather, plus 1/4 plus 1/8. Okay, so you have 1/8, then you have 1/4, and then you have another 1/8. Okay, that's good. Which is equal to 1/2. Okay, so let's have the special case of random variables. The case of several random variables is similar. If the set x sub 1 up to x sub n are discrete random variables defined on the same sample space, their joint frequency function would be, you have the probability of point x sub 1 up to x sub n, which is equal to the probability of the set x sub 1 is equal to the point x sub 1, which up to, uh, the set x sub n equals to point x sub n. Okay, it can be interpreted also as a frequency function, for the random vector, uh, for the random vector, uh, x, set x sub 1, okay, up to, the set x sub n. Okay, so the marginal frequency function of the x sub 1 is actually, uh, the probability of, the point x sub 1, which is equal to the probability of the set x sub 1, which is equal to the point x sub 1, which is actually the summation, okay, the sum, okay, of all the probabilities, okay, from x sub 1, which is equal to the point x sub 1, and then, x sub 2, which is equal to the point x sub 2, okay, up to, uh, set x sub m, which is equal to the point x sub m, in which that would be, from, x sub 2, x sub 3, up to x sub m. So that's our, marginal frequency function of the set x sub 1. Okay, so let's have a review of the double integrals. So we know that the, uh, the integral of the f of x dx from a to b is a distribution to the summation of the f of x, uh, which has the difference of, uh, x sub I, okay, of all x, of all I, given that the interval, AB is the union of all small disjoint intervals, I sub I, such that the x sub I is an element of the I sub I, and the interval, AB is equal to the union, the union of the all i's, okay, which has, a mass of I, which is equal to the difference of the x sub I. Okay, so we denote by the mass. Okay, here the mass, the length of an interval. So this approach can be generalized on two-dimensional domains. Okay, so to illustrate that, um, let D is equal to the a set of the interval xy, or ordered pair xy, which would be the domain in a two-dimensional real number system. Okay, and let the function of xy be a function. So the integral of the f of x, uh, xy dx dy in relation to the d would be, you have there integral the integral of the f of xy dx dy, which distributed uh, to uh, the summation of the f of x sub I y sub I, um, of the delta x sub I delta y sub I. Okay. Now, given that D is approximated by the union of small disjoint rectangles D sub I, such that the interval x sub I y sub I would be the element of D sub I. So, uh, uh, the D is a distribution to the union of all D sub I, which has also the mass of D sub I, okay, which is equal to the uh, delta x sub I by delta y sub I. Okay, so in other words, we denote by the mass. In this case, the mass is the area of the domain. So if the f of xy is equal to 1, then the integral of the uh, f of xy dx dy would be equal to the integral of the dx dy, which is equal to the mass d, where the mass d is the area of the d. Okay, so for calculations, we replace the double integral by repeating integrals. So in this case, let the d would be a set of xy, such that x is an element of AB and y is an element of the alpha x and beta x. Okay, so if that would be the case, then we could have the integral of f of x y dx dy, okay, on the d, which is equal to the integral of dx from a to b, and then integral of uh, f of xy dy from alpha x to beta x. Okay. Similarly, if uh, so let's have similarly if d is equal to uh, here set of xy, such that our y is an element of CD and our x is an element of, let's have uh, sigma y, and gamma y. Okay. Then we could also say in that case that the integral, okay, of d, which is the f of xy dx dy, would be equal to the integral of dy from c to d, integral times integral of the f of xy dx from sigma y to gamma y. Okay, so let's have an example. So let f of x, let f of xy is equal to 1. Then d would be equal to the set of xy such that x is element of 0, 1 and y is element of 0, x. So in this case, okay, in this case, okay, so the integral of f of xy dx dy of the d would be equal to the integral of 1 dx dy of the d, which is equal to the integral of dx from 0 to 1 uh, times the integral of dy from 0 to x, which is equal, in this case, is equal to the integral of dx times x from 0 to 1, which is again equal to x squared over 2. Now, if we are going to have the from 0 to 1, that would be equal to 1 half. And this 1 half is our mass of d. Okay, so note that uh, in this case, the same d can be replaced as uh, d is equal to the set of uh, x, x, y, such that the y is an element of 0, 1, and our x is an element of y, 1. So for f of x, y equivalent to 1, uh, this gives us this gives again some similar to this one. So you have the integral of the f of xy dx dy of the d, which is equal to uh, the integral of dx dy of the d, which is equal to, in this case, that would be um, the integral here, the integral of dy from 0 to 1 times the integral of dx from y to 1, which is equal to the integral of dy times y minus 1 minus y rather, okay, from 0 to 1, which is equal to here na lang, which is equal to negative uh, quantity 1 minus y squared over 2, okay, over 2, which is if we are going to have from 0 to 1, which this is equal to 1 half, which is the same, which is our mass D. Okay, so that's it. So let's have continuous random vectors. Suppose that x and y are continuous random variables with a joint cumulative distribution function, uh, the f of xy. Assume that there exists a function of two variables of the two variables f of xy such that for any reasonable two-dimensional domain D, you have here the probability of xy is which element of D, okay, or belongs to D, is equal to the integral of f of xy dx dy. We say that the function, the function f, is the joint density function of x and y, or the joint probability density, okay, function, which is the PDF of x and y, or uh, the probability density function of the vectors x y. So um, in that concept, clearly we could have um, any density must be any density must be such that the f of xy should be greater than or equal to 0, and then you have the integral from negative infinity to infinity times the integral of f of x f of xy dx dy from negative infinity to infinity is equal to 1. It will be convenient to use the so-called indicator function. We have the I sub I, okay, defined for E set D by the following rule. So we have here the indicator function of x is equal to 1 if x is element of D, and the indicator function of x is equal to 0 if x is not an element of D. The cumulative distribution function, or CDF, of uh, f of xy can be defined as the f of xy, which is equal to the probability of the point x, which is x is greater than equal to the set x, point y is greater than equal to set y, which is equal to the integral from negative infinity to x times the integral of f of uv d dv du from negative infinity to y. Okay. Now, take note that from the fundamental theorem of calculus for the multivariable function, it follows, if you can still remember, it follows that the f of xy is equal to, you have here the squared delta of f over, you have here the delta of x, delta y of the xy. Okay. Similarly, to the case of discrete random variables, we obtain that the distribution of any random variables x or y, or so-called marginal distributions, can be derived from the joint distribution. So the f of the the f of x of the set x is equal to the probability of uh, point x greater than or equal to set x, which is equal to the limit of the probability of the set x greater than equal and set x less than or equal to point x, and then set y less than or equal to point y, uh, which the y approaches to positive infinity, which is equal to the limit of the f of xy, uh, of y approaches to positive infinity, which is equal to the integral of negative infinity to x du, okay, times the integral of the f of uv, dv, from negative infinity to infinity, and uh, the f of y, okay, in relation or with respect to set y, is equal to the probability of set y less than or equal to point y, which is equal to the limit of the probability of the set x less than or equal to point y, set y less than or equal to point y, uh, as x approaches to positive infinity, which is equal to the limit of the f of xy as x approaches to positive infinity, which is equal to the integral of the dv, uh, from negative infinity to y, multiplied to the integral of uh, f of uv du, from negative infinity to positive infinity. So in particular, it follows that the marginal density can be found as, I will write this one here. Um, it follows, it can be found that you have the f of x in relation to set x is equal to uh, the integral of f of xv dv from negative infinity to positive infinity. And the function of y with respect to set y is equal to uh, the integral of uh, f of uy du from negative infinity to positive infinity. Okay, now let's have uniform distribution for vectors. So let set D is a subset of a two-dimensional R be the domain or the region. So let xy be the random vector that has the probability density function uh, f of xy, which is equal to the constant times the uh, indicator function xy. We say that the vector xy is a random vector uniformly distributed in the domain D, or that the xy is uniformly distributed in D. It can be shown that the constant here is uniquely defined from the equality. Okay, from the equality. So, what is that equality? We can have the integral, the integral of f of x y dx dy of the two-dimensional r, which is equal to 1. In this case, it can be rewritten as, okay, it can be rewritten as uh, the integral of f of xy dx dy of the dimension of the d, set d, which is equal to the constant, the times the integral of dx dy of that d, which is equal to 1. So if that would be the case, it gives us that the constant is equal to the inverse of the uh, the inverse of the integral of the dx dy, okay, in respect to d, okay, which is equal to 1 over mesh d. Okay, where the mesh here denotes the area of the domain. Let's have example. The vector xy is uniformly distributed in the triangle D is equal to the set of xy such that x is an element of the interval 0, 1 and y is an element of the interval 0, x. So find the marginal densities. Okay, so for our solution, we have that mesh D. Okay, take note that the mesh D is equal to 1 half. Hence, the joint density, okay, our joint density here, so the joint density is f of x, y, which is equal to the inverse of 1 half times the indicator function xy, which is equal to 2 times the indicator function of the xy. Let me correct. Okay. Further, um, we have that the f of x in relation to set x is equal to uh, the integral of f of xy dy from negative infinity to positive infinity, which is equal to uh, the integral of 2 dy from 0 to x, which is equal to 2x, definitely, where x is an element of the closed interval 0, 1. Okay. And then, okay, and then we could have the f of y in relation to set y, which is equal to the integral of f of xy. Let me correct. Xy. Xy dx. Okay. From negative infinity to infinity is equal to the integral of 2 dx from y to 1, which is equal to 2 times 1 minus y, where y is an element of the closed interval 0, 1. Okay, so uh, it can be seen that the marginal densities are not uniform in this example. So, uh, to verify, sorry, to verify that uh, the integral of f of x, let me correct first. It should not be written that way. The f of x in relation to set x, dx is equal to 1. We have the integral of f of x in relation to x, it must be x, dx from negative infinity to infinity is equal to the integral of 2x dx from 0 to 1, which is equal to 2 times x squared over 2. Okay, then let's have from 0 to 1, which is equal to 1. Okay, so let's have several continuous random variables. We can make the obvious generalization. The joint density function is a function of several variables, and the marginal density function are found by integration. There are marginal density functions of various dimensions. Suppose that xyz are jointly continuous random variable with the density function f of xyz. The one-dimensional marginal distribution of x is f of x in relation to x is equal to the integral from negative infinity to infinity times the integral of f of xyz dy dz from negative infinity to infinity. And the two-dimensional marginal distribution of xy is f of xy in relation to xy is equal to the integral of uh, f of xyz dz from negative infinity to infinity. Okay, so let's have example. One can define random vectors xyz uniformly distributed in the domain the subset of a three-dimensional R. In this case, the density is the f of xyz is equal to 1 over the mass d times the indicator function xyz, where the mass denotes the volume of the domain in three-dimensional R. This definition can be extended on the domains in the n dimension R for any n. Okay, so let's have bivariate normal density. Uh, the definition of the normal random variable can be extended on the multi-dimensional case. So let us consider the two-dimensional case. We say that the pair of random variables x and y has a bivariate normal density if the joint density is given as this one. So you have the f of xy is equal to 1 over uh, 2 pi delta uh, sigma, rather not delta, sigma, okay, times the sigma of y times the square root of 1 minus phi squared times e raised to the power of uh, the 1 times negative 1 times negative 1 over 2 times 1 minus phi squared times the quantity uh, the squared quantity x minus mu of x set x all over the squared of the sigma of the x plus the quantity, the squared quantity of y minus mu of y over the squared of the sigma of y minus the 2 phi, and that phi, that's rho, okay, rho, times the quantity x minus mu of the x times the quantity of y minus mu of y all over uh, the sigma of x times the sigma of y. Okay, so the density depends on five parameters. So you have the mu of x, mu of y, which is an element of R, and then the sigma of x is greater than zero, the sigma of y is greater than zero, and the rho, not phi. I read wrongly on the previous slide. That must be rho. Is an element of negative 1, 1. Okay. So note that the curves in a two-dimensional R where f of x sub where f of xy is a constant are given by circles if the rho is equal to 0, or by elliptic curves if the rho is not equal to 0. Okay. That would be if the sigma of x is equal to the sigma of y. The center of any ellipse or circle is at the point uh, the mu of x, mu of y. So that's it. So let's have the theorem. The marginal densities for the bivariate normal density are uh, n times the quantity of mu of x sigma squared of x, and n times the mu of y squared sigma of y. Okay, so let's have the distribution of independent random variables. Remind that the random variables x and y are said to be independent if for all a sub 1, b sub 1, a sub 2, b sub 2 element of R. So P, or the probability of the set X, which is an element of the half interval uh, a sub 1, b sub 1, and Y is an element of the half interval a sub 1, b sub 1, would be equal to the probability of the set X, which the set X is an element of uh, the half interval a sub 1, b sub 1, times the probability of Y, which Y is an element of the half interval a sub 2, b sub 2. It can be shown that this definition uh, would be equivalent to the following definition. So, what are those? So, the first definition, we have the two random variables x and y are said to be independent if for all x, y element of R, we have the f of xy is equal to f of x in relation to x times the f of y in relation to y. Okay. Here, the uh, f of xy is the joint commutative distribution function for xy, and fx, it must be subscript, not fx. It must be the x here must be subscript, and y here it must be subscript. Okay, are the marginal commutative distribution function. Okay, so uh, it follows that for independent discrete random variables, the joint frequency can be represented as the product of the marginal frequency. So, what are those marginal frequencies? So, we have uh, the probabilities, small letter p, okay, times, not times, the probabilities of xy is equal to the probability of the point x in relation to set x times the probability of point y in relation to set y. So similarly, for independent continuous random variables, the joint density can be represented as the product of marginal densities. So as marginal frequencies, as mentioned, uh, we have not marginal frequencies, marginal densities. So since it's marginal densities, then we can write that one as the f of uh, xy, which is equal to f of x in relation to set x times f of y in relation to y. So these definitions can be extended on the case of joint distribution of n greater than equal to 2 random variables. Okay, so let's have another definition. The random variables x sub 1 up to x sub n are said to be independent if for all x sub I element of the R. So f of x sub 1 up to x sub n is equal to the f of x sub 1 of the set x sub 1 times up to f of x sub n in relation to the set x sub n. So here we have to bear in mind that here the f of uh, x sub 1 up to x sub n is the joint the joint cumulative distribution function, and the f of the x set x are the marginal cumulative distribution functions. Okay. Now, if we are going to have an example of this definition, um, if the set x and y follows the bivariate normal distribution with the rho is equal to 0, their joint density factors into the product of two normal densities. Therefore, the x and the y are independent. Okay. Another example would be if let a random variable x, okay, be uniformly distributed on the interval in the closed interval, let's say a sub 1 b sub 1, and let y, the set y, be uniformly distributed on a closed interval uh, a sub 2 b sub 2. Now assume that uh, the set x and y are independent. Now uh, if we are going to prove that the random the random vector xy is uniformly distributed on the closed interval a sub 1 b sub 1 by closed interval a sub 2 b sub 2. So if we are going to have an illustration, so prove that the random variable xy is uniformly distributed on closed interval a sub 1 b sub 1 by uh, a sub 2 b sub 2, for example, in that case. Now to solve that one, the random variable x the random variable x has a density of, if we are going to solve that one, the density of f of x, uh, it must be f. So let me check. F, okay, in relation to set x, okay, is equal to the constant times the indicator function, okay, in a closed interval a sub 1 b sub 1, okay. So that function would be of y, and then the random variable, the random variable y has a density function of f of y in relation to y. It must become with a letter because It's a set. Okay. Now is equal to the constant times the indicator function. Very far. The indicator function in the closed interval a sub 2 b sub 2, and this would be y. So it follows from uh, independence assumption that the random vector xy has a density uh, f of xy is equal to f of x and f of x in terms of y in terms of x times the f of y in terms of y. Hence, the the f of xy would be equal to the constant times the random the times the indicator function of the xy in terms of the closed interval b a sub 1 b sub 1 by a sub 2 b sub 2. Okay, so by the definition, this vector is uniformly distributed on the corresponding rectangle. Okay, so let's have mixed case. So mixed case, so let the x distributed to the u on 0 1 uniformly on close interval 0 1, and y has a Bernoulli distribution with parameters p is equal to one third. So for example, you have the probability of y equals 1, which is equal to one third, and then the probability of y equals 0 is equal to two thirds. Then the joint distribution is not either, is neither discrete nor continuous. So if x and y are independent, then the joint uh, commutative dis, distrib, commutative distribution function is f of xy is equal to f of x in terms of x times the f of y in terms of y. Okay. So conditional frequencies. Okay, consider the discrete random variables x and y with the uh, joint frequency of p of xy with the marginal frequencies of uh, p of x in terms of set x, and this must be subscript. Okay, p of y in terms of set y. By definition of the conditional probability, we have the conditional uh, probability of xy, okay, is equal to the probability of x equals point x, and then set y is equals y over the probability of y over uh, y equals the point y. Now, if you can still remember with the conditional probability in our basic education or even in our college days, uh, we are very familiar with this kind of formula. So the conditional probability, okay, a is equal to the probability of uh, a and b over the probability of a. So this is actually similar to each other. So therefore, the conditional frequency function can be defined as you have here the probability of the probability of uh, xy is equal to the probability of xy. Okay, conditional probability. This is a conditional probability of xy is equal to the probability of xy over the probability of y of the set y. Okay. This probability is defined to be zero if the probability of y in terms of set y is equal to zero. Okay. note that this function is genuine frequency function since it is non-negative and the sum is equal to 1. Okay, so it can also be seen that if the set x and y are independent, then the conditional probabilities of xy is equal to the uh, probability of x in terms of y, in terms of the set x rather. So in this case, the knowledge of the value of y does not change our estimates for the probabilities related to the values of x. So uh, it follows the definition that the probability of I will write this here. So it follows the definition that the probability, okay, of xy is equal to uh the probability of the conditional probability of xy. Okay, so in terms of the conditional probability of xy times the probability of y in terms of uh, set y. And because of this definition, we could have the probability of x, okay, in terms of the set x. Let me write it neatly. Would be equal to the summation of the conditional probability of xy in relation to conditional probability xy. Y, not p, times the probability of y in terms of set y. Okay, so let's have conditional densities. So let x and y, the set x and y, be continuous random variables with the joint density f, uh, and with the marginal densities, it must be subscript, and this must be x. Oh my god. So let me check. Let me correct. So by definition of conditional probability, we have for small uh, dx and dy that the probability of x, which is the x's element of the interval x x plus dx, which is a condition probability, okay, of y, and here y is an element of the interval y to y plus dy, which is equal to the probability of the x, which the x is element of the interval x x plus dy, and then dx rather. Then y is element of um, the interval y y plus dy all over the probability of y, which the y is an element of the interval y y plus dy. This is can be written as uh, the integral from x to x plus dy, x plus dx rather, times the integral of f of uv dv du from y to y plus dy all over the integral of the f of v dv in terms of set y from y to y plus dy, which is approximately equal to the f of xy dx dy over f of y dy in terms of set y. This value is proportional to the x. Therefore, since they are proportional, uh, the conditional density. Okay, the conditional density function can be defined as f of uh, the conditional density function, uh, f of conditional xy, okay, in terms of the set x conditional y, is equal to f of xy over f of y in terms of set y. It can also be rewritten like f of conditional the condition, this is conditional density function, f of xy in terms of the set xy is equal to f of the conditional uh, xy, where y is equal to the point y in terms of x, meaning that the f of uh, conditional x y, where y is equal to point y in terms of x, is the probability distribution function for x under the conditional probability given that y, the set y is equal to the point y. This means for any interval a subset of r, we have the probability of the set x, which the x is element of the conditional ay, where y is equal to point y, which is equal to the integral of the f of the conditional xy, where y is equal to y dx, okay, in terms of the set A. Okay, so note that the uh the this one, okay, this one, okay, is equal to f of x in terms of x if x and y, or if the set x and set y are independent. In this case, the knowledge of the value of y does not change our estimates for the probabilities related to values of x. Okay, so let's have Bayes' formula for densities. So it follows uh, the definition that f of xy is equal to the uh, conditional frequency of xy in terms of set x and y times the times the f of y in terms of y. Hence, the f of x in terms of the set x is equal to the integral of f of xy dy from negative infinity to infinity, which is equal to the integral of f of the conditional function f xy, okay, from in terms of the conditional set xy, okay, times the f of y dy in terms of the set y from negative infinity to positive infinity. So the these would be the theorems which gives us analogs of Bayes' formula for continuous distribution. So what are those formulas? Definition that theorems rather. So So this would be the theorem. So let A be subset of R, be an interval. So let the set xy be the random vector with the joint density f of xy. Then y is the marginal density uh, f of y in terms of y. Then the probability of x element of A is equal to the integral of the probability of x, which the x is element of the conditional uh, conditional set a y, where y is equal to point y, okay, times the f of y in terms of set y dy from negative infinity to positive infinity. So in this case, the probability of x as x element to A would be uh, equal to the integral of f of x in terms of the set x dx, in context to a, which is equal to the integral of dx times the integral of the f of the the conditional frequency xy, okay, in terms of the conditional set xy, okay, times the f of y, okay, in terms of y dy from negative infinity to positive infinity, which is equal to the uh, integral of f of y in terms of set y dy, from negative infinity to infinity, times the integral of the f of the conditional frequency, a conditional function of xy, okay, in terms of the conditional set xy dx, which is equal to the uh, integral of f of y in terms of set y times the probability of x, which the x is an element of the conditional set a y, where y is equal to point y from negative infinity to positive infinity. Okay, so let's have another theorem. Okay, so let D be an element of a two-dimensional R, be the domain. So you have x, y, be the random vector with joint density of f of xt, and y has the marginal density of f of y in terms of the set y. Then the probability of xy, which the xy is element of D, is equal to the integral of the probability of xy, which the xy is an element of the uh, conditional y, where y is equal to y, point y, times the f of y in terms of set y dy from negative infinity to positive infinity, or to infinity. So if we let dy, so let's write this one. Let d uh, of y is equal to the set x, such that such that uh, xy is an element of the d. Then what we have here is the probability of uh, x. It must be capital letter xy element of d is equal to the integral of f of xy dx dy, which refers to the d, which is equal to the integral of f of uh, conditional x y. So this is also conditional f times the f of y in terms of set y. So here you have dx dy, which is equal to uh, the integral of uh, f of y in terms of y dy from negative infinity to infinity, times you have the f of the conditional uh, xy in terms of the conditional set xy. It must be capital letter dx. Okay, which this um, refer to d of y. Okay, so furthermore, we could have the p is equal, this must be capital letter, mhm, of the x, y element of the d conditional y, where y is equal to point y, which is equal to the probability, capital letter, of x element. It must be capital letter, not small letter. It must be capital letter. Element of uh, d of y conditional to y is equal to point y, which is equal to the integral of f of x, y. This is a small letter because that's a point. In terms of x, y, capital letter, dx. In terms of y, a d of y. Okay, so that ends the presentation.